So, good evening, Carmarthenshire. This is the Science of Santa, a short and rather tongue-in-cheek talk about science and whether or not Santa disobeys any of the rules, the laws, as we understand them. So, is Santa compatible with the laws of physics? That's the question. Or, if you turn it around, how many laws of physics does Santa actually break? So we know that Santa is, allegedly anyway, a portly jolly fellow with a white beard and a penchant for wearing red suits. And although that gives rather questionable fashion sense, that doesn't really mean he can't exist. So what about the claims that are made for Santa? And we're going to look at those and ask about the laws of physics. So the claims that we're talking about are that Santa, allegedly, visits all households on Christmas Eve to deliver presents to all qualifying children. And qualifying, of course, is determined by his naughty nice list. So can we reconcile this particular set of feats with our understanding of the laws of physics? And in particular, can we use anything that I've said in any of my other talks regarding descriptions of science that can actually help us understand whether Santa should be allowed by the laws of physics or not? So I've given a number of different talks. Here's a sprinkling of them. And I'm going to see if any of what I've said in any of these talks has any bearing on the existence or otherwise of Santa. So let's just remind ourselves of the sentence that we are going to try and unpick and see if it makes any sense. This is the statement we're addressing. Santa visits households on Christmas Eve to deliver presents to children. And we're going to take that one little bit at a time and see what are the consequences. So let's start with the children that he visits. Basically, let's start with how many. How many children get presents at Christmas? Well, the Earth's population is about 8 billion or so. Scary, but true. And about 1/4 of the Earth's population are children. Now, I'm just taking children as anybody who's not an adult, regardless of whether they believe in Santa or not. 50% of the children are eligible for Christmas presents. I'm assuming that's simply because Santa is quite generous and doesn't worry too much about the religion of the household. A number of students will still get Christmas presents. So we're talking about Santa delivering presents to about 1 billion children. Again, that's assuming a particular ratio of the naughty nice list. Let's just, for the sake of argument, assume no children are naughty. That might be a bit of a push, but yeah. Let's assume no children are naughty and they're all on the nice list. So Santa has to get round to 1 billion children. Okay. Right. How does he actually achieve this visitation? Well, we have to think about transport. How does he get around? He gets around in a sleigh pulled by flying reindeer, apparently. So the question is, can reindeer fly? And we look around and we see that insects can fly, and we see that birds can fly, and we see pterosaurs that fly. Well, you don't see many pterosaurs these days. And we know that some mammals can fly. So the question is, this particular mammal, can this one fly? Can reindeers fly? Well, if they can fly, it seems they choose not to do so for a lot of the time because we have no direct evidence that they can fly. We don't see any photographs, we don't see any video, we don't see David Attenborough talking about flying reindeer. But in science, you have to remember that the absence of evidence is not evidence of absence. Just because we don't have evidence that they do fly does not mean that they don't or cannot fly. So in other words, the jury is entirely out on flying reindeer. Okay, how fast would Santa have to go in order to visit all of these children? So to visit 1 billion children in one night, remember a night is not simply 12 hours. The length of darkness would be more than 12 hours in the northern hemisphere and less than 12 hours in the southern hemisphere, but Santa can take advantage of the time zones around the world, and so if he plans his trip correctly, he's got about 36 hours in which to visit all the children in the world. Rather than worry about exactly where they are geographically, let's just sort of spread them over the land surface of the Earth and assume a lot of them are in cities. Santa would have to travel at some 2,000 kilometres per second in order to visit 1 billion children in one night. And although 2,000 kilometres per second sounds like a lot, it is trivial. It is less than 1% of the speed of light. And that, of course, is the only speed limit that physics actually imposes on people moving around or objects moving through space. So even at that speed, Santa would not be in any danger of defying any of the laws of physics. In a talk I call Fiat Lux, I actually measure the speed of light as well as measure wavelength of light and other things like that. And it's a reminder that no object can travel through space at a speed greater than the speed of light in a vacuum, but at a speed of 300,000 kilometers per second, Santa is going much, much slower than that. So no problem at all up to this point. But if he is going really fast, wouldn't the sleigh and perhaps the reindeer burn up? Wouldn't be looking at roast reindeer at some point if he's moving at 2,000 kilometers per second? Well, just as a meteor coming into the Earth's atmosphere or a large rock like an asteroid entering the Earth's atmosphere, they would compress the air in front of the object that's moving so fast, and when you compress air, it heats up, just like when you're pumping up a bicycle tyre. So again, in a different talk, I talk about the ABC of stellar evolution and how this relates to stars, and the C of the ABC is precisely what we're talking about here. Compression produces heat. That's what produces the heat in the core of a star. And if we've got an object moving through the atmosphere very quickly, the compression of air in front of the sleigh would presumably heat up the sleigh and the reindeer and presumably Santa and all the presents as well. Even if the sleigh was aerodynamic, that wouldn't be enough to make sure that it didn't warm up under the compression of the air in front of it. So, if the sleigh is moving fast through the Earth's atmosphere, shouldn't it be glowing white hot under the heat generated by that fast motion? Well, we know that compression produces heat, and we know that hot objects generally radiate light. If they're really hot, they'll be generating a white hot glow. So Santa and his sleigh, if they're moving at that speed, ought to be easily visible. And the question is, are the sleigh and Santa and reindeer easily visible? Well, you could argue that they have been seen before, but it's a bit of a long shot to say that the Star of Bethlehem was actually Santa, because the timing doesn't really work out right, does it? But when we're talking about bright lights in the sky, well, some people would say, yes, we see those all the time. There's plenty of UFOs, and it's easy to mistake Santa's sleigh as a white dot flying through the sky at great speed as being an unidentified flying object. But there's an alternative, because we do know about some materials, some matter, that does not emit or indeed reflect any light, no matter how hot it gets. It doesn't emit or reflect or absorb any electromagnetic waves. So most ordinary matter, the sort of stuff we see around us, if you heat it up, it glows eventually red hot if it's hot enough, and if you keep heating it up, it'll glow white hot. But there is matter in the universe, we think, called dark matter, which does not glow when it gets hot. So maybe Santa and his sleigh are made of this mysterious dark matter. We think dark matter is out there because of the way things behave, the way stars move, the way galaxies move. We deduce the existence of dark matter even though we can't see it, because it doesn't glow like stars do. They don't produce light, and therefore we can't see these clumps of dark matter. And we're not even sure where the dark matter exists. We just know it's out there somewhere. So maybe that's the explanation. Santa and his sleigh, and perhaps his reindeer as well, are made of this mysterious dark matter. We need more research to find out what this dark matter actually is. That, incidentally, also explains, if it was made of dark matter, that explains why the sleigh does not show up on radar, because any attempt to get a reflection on radar, the radar would simply go through the sleigh, would not reflect off it to produce a radar ping. Let's have a look at the next thing we're trying to deal with. We've talked about children, we've talked about visits. Now let's think about the households that Santa has to visit. How can Santa get down so many chimneys so quickly? If you want to visit 1 billion children in one night, then Santa would have to go down something like 3,000 chimneys each second. And remember that if Santa is a jolly but rather portly gentleman, then that's going to be a bit of a problem. But the laws of physics actually come to our aid at this point, because the rules that dictate how atoms behave, the so-called rules of quantum mechanics or quantum theory, tell us that atoms are made of a positively charged nucleus and negatively charged electrons buzzing around that nucleus. Hypothetically, if we were to replace the electrons in every atom in Santa with a heavier particle called a muon, which is a little bit like an electron but just a heavier version of the same thing, then all the atoms would be some 200 times smaller. And if all of Santa's atoms were 200 times smaller, that means Santa himself would be 200 times smaller. So instead of being a gentleman a little less than 2 meters in height, he would only be a centimetre or 2 in height. And of course, if you're only a couple of centimetres tall, then getting down the chimney would be no problem whatsoever. So exactly how Santa would replace all the electrons in his body with muons, I don't know, but it's allowed according to the laws of physics. But maybe there aren't chimneys. Remember, there's plenty of houses and apartments that do not have a chimney. So how can Santa get inside a room unless he has access through a chimney? Let's assume people don't leave their doors and windows open. Well, again, quantum mechanics comes to the rescue, because we look in the quantum world at subatomic particles and atoms and molecules, and we find it is possible for a particle, such as an atom, to go from one place to another without passing through the intermediate space. In other words, it's effectively possible for an atom to go from outside a box to inside a box without ever penetrating the walls, in the sense of going through a gap in the walls, going through an open door, going through an open window in the case of a room. So if it's possible that atoms do this, and in principle physicists see this happening all the time, if it's possible for an atom to do this, then given that Santa is made of atoms, why can't Santa do the same? Why can't he just, almost by magic, but no, through the laws of physics, a process called tunneling, why can't Santa tunnel his way from the outside to the inside without needing an open door or an open window? Okay, so that's allowed as well. So we've talked about children, about visiting, and about households. All of this done on Christmas Eve in one night. How can Santa make so many deliveries all in one night? Even at travelling at relativistic speeds, at a fraction of the speed of light, how can everything be done in less than 36 hours? Quantum mechanics yet again tells us this is perfectly okay. When we examine how atoms and molecules and subatomic particles work, we find that the rules of physics allow a particle to be in 2 places at one time. Doesn't make any sense as far as common sense is concerned, because we don't normally see that happening in the world around us. When we look at a cup of tea standing on the table, it seems to be in one position or another. It doesn't seem to be in 2 places at once. But when we look at the world on a much finer level, with microscopes that tell us how things are behaving, we find that according to the rules that we understand, it is possible for a particle to be in 2 places at the same time. So again, because Santa is made of atoms and atoms behave this way, why can't Santa be in 2 places at once? Or 3, or 4, or 5 million? So it doesn't seem to break any laws of physics for that to happen. So there's no problem with Santa making lots of deliveries in one night. If for some reason you believe that Santa could only be in one place at a time, there's no need to assume that. But if you said Santa can only be in one place at a time, then he'd need an alternative way of making those deliveries. In other words, Santa would have to be capable of somehow manipulating space and time. In other words, you can go to lots of different places if you make them a lot closer together. You would have to stretch or squeeze the space in between two different locations in order to bring them closer together, to make it easier for you to visit lots of different places in one night. And again, we believe that is actually happening. Einstein's general theory of relativity says that space is not simply a load of gaps in between the stars. You should think of it more like a sort of a jelly which can be distorted and stretched and squeezed. And the presence of massive objects like planets or stars or galaxies can distort space. Maybe Santa has figured out a way of doing that as well, in order to bring all the houses that he has to visit closer together. So we've thought of children and visits and households and doing it all on one night. But we also have to consider how he can deliver all of these presents to these children. How could Santa carry all the presents? Remember, we're talking about 1 billion children. Let's assume they get one present each. So how can the sleigh hold 1 billion presents? Well, one solution, again, is to warp space. The sleigh, in principle, could be bigger on the inside than it is on the outside. We all know about Doctor Who's TARDIS, which is bigger on the inside than the outside. There's no reason why the sleigh can't be the same. There is a precedent for this because, for instance, black holes, okay, we don't have any in our local neighbourhood, but we do know that they exist. A black hole is bigger on the inside than it is on the outside because of the way matter distorts space. So if it's possible for mass to distort space in such a way that a black hole is bigger on the inside than it is on the outside, maybe Santa has figured out a way of getting the sleigh to do the same thing. So even though the sleigh only appears to be a few meters in size as seen from the outside, maybe on the inside it's actually huge and easily big enough to take 1 billion presents. So again, the rules of how space and time behave according to Einstein is perfectly consistent with a sleigh that can hold 1 billion presents. There is an alternative, again, for those that don't like the idea of that particular solution to the problem, and that is that we actually don't know how many dimensions there are in space. We think there are 3 because those are the 3 dimensions that we can perceive: forward, backward, left, right, up, down. But many physicists believe there are actually more than 3 dimensions, and it's simply that we can only perceive 3 of them. So maybe there are more than 3 dimensions and Santa has figured out a way of accessing these dimensions. So all that's required is to take the presents with you, push them into these other dimensions, fly to where you want to go, and then when you need a particular present for a particular child, you just pull them out of that dimension back into our 3 dimensions and then put the present under the tree. It might be that you've got lots of dimensions to choose from. It might be there aren't just 3. It might be that there are 10 or 11 different dimensions. So Santa has got a lot of space, if you'll excuse the pun, into which to store all of these presents. Maybe that's the way he does it. But you might say, okay, maybe Santa does this, maybe Santa does that. But wouldn't all of these explanations need a huge amount of energy? If he's going really fast, Santa and the sleigh and 1 billion presents, all moving at a fraction of the speed of light, surely this would just need so much energy. This would be prohibitive because there's no way Santa would have access to that huge amount of energy necessary to do all of these things. Well, maybe. But if a black hole could power a starship and send it to the stars, which we believe it can, hypothetically, why couldn't a black hole power a sleigh as well? So I don't know if Santa simply has brought a black hole along and has placed it in the back of the sleigh and he's using that as a power source. If he did, that would give him a huge amount of energy to play with, just like you could in principle use a black hole to power a starship and reach the stars very quickly. Perhaps that's the way you power a sleigh. But there's an alternative. We don't have to use a black hole. There is an energy source that we're overlooking. It's the elephant in the room. It's something we haven't mentioned yet. And that is, what happens to all the mince pies? If a fraction of households leave a mince pie out for Santa and he's visiting a billion children, there's an awful lot of mince pies. Now, no one in their right mind would think that Santa eats them all. Surely not. What if Santa could convert the mass of all of these mince pies into energy? Einstein has told us that there's an equivalence between energy and mass according to E equals mc squared. If you've got a given mass and you convert it into energy, you take the mass, multiply it by the speed of light squared, and you'll get the equivalent amount of energy. So what if Santa had access to all of the mince pies and somehow could convert them into energy? Then he'd have more than enough energy in order to do all of the things I've been describing. Let's calculate it. I'm a physicist, so I love doing calculations. Right, what's the mass of one mince pie? One mince pie is about 50 grams. So the energy that you could extract from the mince pie is mc squared, where m is 50 grams and c squared is the speed of light squared. That comes out to be a number of 5 times 10 to the 15 units of energy, called joules. Yes, I know you're not familiar with what a joule is. I'll come back to that in just a moment. But first, let's multiply by the number of mince pies he might have available to him. Let's assume that not everybody leaves mince pies out for Santa. Let's assume it's just a few % of households that he visits that leave him a mince pie. So if it's a few %, let's say 20 million or so mince pies, then the total amount of energy would be 20 million times the number I've just calculated. So the total energy available to Santa during the course of the night would be 10 to the power 23 joules. Now we need to put that into some sort of context because nobody knows what 10 to the power 23 joules actually means. That's approximately the total amount of energy that you would expect to come out of a nuclear power station if it ran, not all night, if it ran for 1 million years. So imagine a nuclear power station generating a gigawatt of power, add up all the energy it generates in 1 million years. That is the amount of energy that Santa would have available if he could extract all of the energy from the mince pies. Plenty of energy to send him around the world at very high speed and do all of the things that I've been talking about. So then you have the question, of course, how do you extract the energy from a mince pie? Well, I'm not too sure, but there are some possibilities. One option is you take a mince pie and you collide it with an anti-mince pie, and you do that in the Large Mince Pie Collider, which is situated in CERN. Now, that gives you an awful lot of energy, but of course it raises the problem, where do you get the antimatter mince pies from? So yes, that's a little bit of an issue. Is there an alternative way of getting lots of energy out of a given amount of mass? And yes, there is. Without invoking the existence of antimatter, there's an alternative way. You can't get all of the energy out, but you can get a fairly big fraction of the energy out of any matter by dropping it into a black hole. We've actually seen this in the sense that we can see objects in the universe called quasars. These are the centers of very energetic galaxies that are emitting huge amounts of energy. And we think they're getting their energy from matter that's falling in to the very massive black hole at the center of a quasar. Now, the matter that's falling in is probably not mince pies, it's probably gas and dust and probably stars that are falling into the black hole and generating huge amounts of energy. The energy output is so vast that some of these objects can be seen. In a separate talk, I've talked about how I can photograph one of these quasars. Even without a telescope, it's possible to photograph one of these quasars because they're producing so much energy, they can be seen even though they are on the other side of the observable universe. That tells us just how efficient it can be to drop matter into a black hole and then convert most of that matter into energy. So we know it's possible. How much energy do you get when you drop a mince pie into a black hole? I found it very difficult to find out, in the sense I could not find anybody doing research in this area. So there's very few papers being published on mince pies being thrown into black holes. But I'm sure it's possible, and I'm sure it produces a lot of energy. How could Santa actually do all of that? How could Santa either warp space and time, or how could he control black holes? How could he ensure that he can get around the world and do all of these things in one night? Well, one thing you have to bear in mind is that although all of these possibilities are allowed by the laws of physics, the idea that Santa could do this, just because we don't know how he might, for instance, be able to manipulate space and time, just because we don't understand how he does it, doesn't mean he can't. And remember, who says Santa has to be human? Maybe Santa, remember, nobody's actually seen Santa. Everybody's asleep when he visits. So maybe Santa is capable of manipulating space and time in ways that we simply do not understand. So remember the question we were trying to answer: how many laws of physics does Santa actually break? I think the answer is none. So feel free to draw your own conclusions about the existence, or otherwise, of the portly, jolly fellow with the white beard and a penchant for wearing red suits. Regardless of your conclusion, I'd like to wish you all a very Merry Christmas. Thank you very much for listening.